Hello viewers, welcome to this next lecture of our series of lectures on solid state. In today's session, we will talk about closed packed structures. The session is planned as follows. To begin with, I will quickly recall what we did in the previous session. Thereafter, we will talk about why do we need to talk about closed packed structures. This will be followed by the closed packed structures in 2 dimension. Thereafter, we will try to see closed packed structures in 3 dimension. And in the process, we will come across the meaning and location of trigonal, tetrahedral and octahedral voids. Thereafter, in this whole process of talking about closed packed structures, we will try to learn about that AB repeat and ABC repeat and the corresponding unit cells in that. Having done all that, then towards the end we will try to sum up what we do today. Let us begin by recalling what we did in the previous session. We started with describing different types of Bravais lattices. Thereafter, we discussed in detail the cubic unit cells in terms of the location of lattice points, types of lattice points and their contribution to the unit cell. That means, which lattice points contribute how much to the unit cell. Thereafter, we computed the atomic packing fraction of different types of cubic unit cells, that is simple cubic, body centered cubic and face centered cubic. Thereafter, we explained the approach for computing the density of a crystalline solid from the unit cell dimensions, that is the edge length and the lattice type, whether it is simple cubic, body centered cubic or face centered cubic and so on and so forth. Having done all that, now let us make a beginning for what we want to achieve today. We start by raising the question, why do we need to talk about closed packed structures? The answer to that comes from here. Basically, when we talk about closed packed structures, essentially we will be referring to that if I take spheres, identical spheres, if they pack them, then what kind of structures do we get there? And the rationale for this comes here, that because for all practical purposes, the atoms can be considered to be spherical in shape. That is why we are talking about using spheres as the materials to build up our structures. Secondly, the close packing of equal sphere gives a dense infinite regular arrangement, because that is very important. Because if you remember that when we talked in the previous session, we talked about the atomic packing fractions, we realized that FCC lattice gives you about 74% of packing. That means the atoms occupy about 74% of the space there, and in general nature always tries to make things very economical. We will come to that point later also. Thirdly, that the closed pack arrangement, you take spheres and try to pack them in different possible ways, the one which has got closed pack structures will give you highest packing density, that means using the space to the maximum. Lastly, the most important aspect here is the crystal structures of most of the metals and many other crystalline solids can be rationalized in terms of closed packing. So, that is our driving force. Two main things: the first point, that atoms can be considered as spherical in shape, and lastly, since the structure of many crystalline materials and most of the metals can be rationalized in terms of closed packing. So, we need to talk about closed packed structures. So, let us begin by talking about closed packed structures in 1 dimension. What basically it means is that we take identical spheres and put them all together, link them together, so that you get a row of spheres that will look something like this. Now, if we have got this kind of a layer, that is this kind of a row, this is identical spheres which are into 1 dimension there. Okay. Now, suppose I want to now extend further, I want to go to 2 dimensions. So, what do? I take one row of identical spheres, take another row, put on top of that, yet another one, and in this process I can generate a 2-dimensional structure there. Let us have a look at it here. I have got one row. What do? I take another row here and put it on top of it. So, there are 2 rows there. I can take third row, bring it here and keep doing that. So, in the process what I will be getting is, I will be getting a square closed packed structure. That is one kind of a packing in 2 dimension. Alternatively, what we can do is that I take one row and then take the second row in such a fashion that the second row slides into the grooves of the first row. That means, this was the earlier arrangement where I got a square close packed structure. Now, I move it like this and pack it into the crevices of the first row. So, what do I get is I get a different kind of a pattern here. Such a built up, that means, if I take one row, put on top second one, third, keep on building that. So, what I will be getting is I will be getting what is called as a hexagonal close packing. Let us try to compare these two packing systems. So, in the first case what we had was square close packing, that is a kind of a unit cell we are generating here, or in other words we can see that if I take any sphere here, this is directly in touch with 1, 2, 3, 4. So, there are 4 neighbors to that. So, it is a square kind of a packing there. Whereas, in case of hexagonal close packing system, what do we have? There is one sphere here. So, this is directly in touch with 1, 2, 3, 4, 5, 6. That means, there are 6 neighbors. Such a packing is called as hexagonal close packing in 2 dimension. Now, let us try to compare the two kind of systems here. So, what I have done here is that I have taken equal number of spheres in both the cases. So, visually also we can make out here that this kind of a hexagonal close packing is more economical in terms of space as compared to the square close packing, which in fact is true. That means, in 2 dimensional HCP, hexagonal close packing in 2 dimension is more economical, space economical as compared to square close packing in 2 dimension. Since our hexagonal close packing in 2 dimension is more economical and most of the crystals follow this kind of a packing, let us try to learn little more about it. Let us have a relook at this kind of a packing. What you find is that hexagonal close packing has got 2 types of trigonal voids. What you see is that when you got one row, another row covering it on the crevices of that one, and so on and so forth, when this builds up, you get blank spaces, the voids here, and these voids, if you look closely, are of trigonal shape. Let me just show it to you. I am just taking a small part of it. Let us understand that. Now, suppose I have taken a small portion of such a layer. What do I find here is that in this layer, this is my first row, second row, third row. I have just taken a few atoms of the rows. What I find is that these are the gaps. That means, when one row, the second row covers the first row, there is some kind of a small gap created here. These are the voids I am talking about, because they look triangular in shape, they are called as trigonal voids. And if you look at this void and the next one here, we find that there is a difference between the two. In this case, such a void, we find that the vertex is pointing downwards, whereas in this void the vertex is pointing upwards. So, such a void wherein the vertex, as a tip of the triangle, is pointing upwards is called as A type of trigonal void. This is called as the B type of trigonal void. This A, B are very arbitrary. We can even call it as X type, Y type, and so on and so forth. It's your choice. Some people use it as P, Q, some people use X, Y. So, that's nothing hard and fast about it, but typically most of the people talk about in terms of A, B. So, I am using A and B type of trigonal voids here. So, that is, if I look closely, there are 2 types of trigonal voids. That is what you have seen in case of hexagonally close packed layer. Now, if I move further, that means this picture clarifies the 2 types of trigonal voids, that is type 1, type A, so to say, the vertex is pointing upwards, and type B, vertex is pointing downwards, which I just showed you. Suppose, because I have to build up a packed structure in 3 dimension, to go into 3rd dimension, because from a row to a layer I have covered the 2 dimensions here. But if I want to go to the 3rd dimension, I have to take one layer, put another layer on top of it, and then go on building up on that. So, what I am now going to attempt is that if I take my first hexagonally close packed layer and try to put a second layer on that, what do I get? Let us have a look at it. So, this picture tells you, shows you that this is my first layer, the back layer here, and the front layer is the second layer which I put on the top of the first layer. So, basically this is one layer here, another layer on that, what this picture is showing you the top view of that. Now, if I look at closely, what you find what you find is that when I am trying to put my second layer on top of the first layer, there is only one way of doing it. That is, either I will occupy A type of trigonal voids or B type of trigonal voids. I cannot occupy both the type of voids simultaneously. You can even do it on your own. I can suggest to you is that you take, say, 1 rupee coins. Take 1 rupee coins, arrange them in the form of a hexagonal close packed layer, and then you can even visualize that trigonal voids there. Thereafter, when you are trying to put a second layer, try to occupy any one type of a trigonal void. You will find that the other type, the neighboring other type of trigonal void, suppose I have covered the A type, the neighboring B type cannot be occupied, because that means there will be overlapping of the spheres, which are not to be done, because they are not to be allowed, because we are just trying to do close packing. There is no squeezing in, there is no overlapping over there. So, automatically they get avoided here. So, the picture I am showing you here, in this case what I have done, I have occupied type A of the trigonal voids, which is visible because the second layer shown here is made transparent, so that we can see here that behind it there is a type of trigonal void. So, if I do that, so what I am getting is I am getting a top view of the second layer which is occupying the first layer in such a fashion that the A type of trigonal voids are covered by this. Now, by doing this, we have done lot of things here. Let us understand, let us try to have a look at these two things closely, because they are going to give us lot of information about the intricacies, the intricate structures of the close packed structures. Now, have a closer look top view of that. What I have done is I just tried to blow it up. When I try to blow it up, what I find is that if I take a closer look, you find that there are structures of this kind, hexagonal kind of things are forming here. These are actually octahedral voids. These kind of structures will be formed when, now suppose I have my first layer. In the first layer there is a trigonal void, okay, say type A, and from second layer another trigonal void comes and sits on that, the opposite part of it. That means suppose this is A type, B type comes and overlaps that one. So, between the two trigonal voids there will be a space which will be octahedral in shape. Such a void is called as octahedral void. That is what exactly is being shown over here. So, that means this space here, this space is indicative of the space between the two layers. There is this one layer, the second layer, the space in between the two. Let me try to show it to you with the help of a small model here. Say this is my one layer, say layer A or layer 1, and this is my layer 2. So, what I am doing is I am showing you, suppose this is what my layer A, first layer. In the first layer this is a trigonal void of type A, that means the vertex pointing upward. On this I put my second layer in such a fashion that you have a trigonal void here whose vertex is pointing downwards, that comes and sits on that one. Now, when that happens, so what you get is right between here, between the two places, you can see it from the side here, that is a void, that void is your octahedral void, because there is one trigonal void, another trigonal void of opposite type, the two are overlapping and generating a octahedral void. So, you got octahedral void, as has been telling again and again that octahedral voids are formed by overlapping of a given type of trigonal void by a trigonal void of opposite type. That means, if I have an A type covered by the B type, I will get an octahedral void, or vice versa. So, what I am showing you here is, so in this case I have taken only 3 atoms each of the 2 layers. So, in this case this is a B type trigonal void covering A type trigonal void. So, I am getting is a octahedral void right here. So, I have just put 2 layers of different colors, so that I can differentiate between the two. Similarly, in this case I have got A type of trigonal void covering the B type of trigonal void, and here again I am getting a octahedral void. So, that means if you have a atom here in this void here, so that will be in touch with 6 spheres. So, what you see is, that is, if you have a trigonal void, say here, if you have got a trigonal void and suppose one atom comes and sits on that. So, there are 3 neighbors here, okay, because I do not have to use such a big one. Suppose there is a small atom comes and sits on this. So, that is in touch with the 3 neighbors here, But suppose I have got two trigonal voids, one of this type, one of the other opposite type, and we have got a small atom inside there, that will be in in touch with 6 atoms there. So, there are 6 neighbors. Anything which is in this octahedral void will have a coordination number of 6, since there are 6 neighbors to that. Let us go on to have a fresh look at the top of the second layer. When I look at that, what we find is that besides the octahedral voids which we just discussed, there are other types of voids there, and these voids are the ones which are created by covering of a trigonal void by one atom, or covering of one atom by another trigonal void of the neighboring layer there. That means, you have got a situation of 3 on 1 or 1 on 3. Let me explain to you. Now, what you find here is that in this case of 3 on 1, what do we have? You see that there is an atom behind it, that is of layer 1, and then these 3 atoms of layer 2 are overlapping that. So, what you are getting is this is space in between, that is my tetrahedral void. Let me just show it to you with the help of a model here. Say this is my one atom I have taken of first layer, and there are the 3 atoms or a trigonal void of second layer. Okay. So, when I am trying to put on top of this, so what happens is that is there is one atom, and then this trigonal void is covering on that, and what I am getting is there is a space created in between, and this void here right inside here, that is the tetrahedral void. That is one possibility. Second possibility is that I have got 3 atoms of my first layer, and from the second layer one atom comes and sits on the top of the trigonal void. So, what I am getting is I am getting another type of tetrahedral void. So, there are 2 kinds of tetrahedral voids being formed here. I will elaborate more on this as we proceed, but I am sure that you are able to visualize that when I put second layer, second hexagonal close packed layer on top of my first hexagonal close packed layer, I get variety of voids there. There are octahedral voids and there are tetrahedral voids, and the tetrahedral voids are of 2 types. As regards octahedral voids, they all are identical. Let us move little further. Let us move little further and have a look at the tetrahedral voids. I have just explained to you, that is, you have one atom of the previous layer covered by 3 atoms of the second layer, or 3 atoms of the first layer covered by 1 atom of the second layer. In both the cases, I am getting a tetrahedral void, but they are of 2 different types. We will elaborate more about it as we proceed. So, what we see is that tetrahedral voids result from the overlapping of a trigonal void of by a sphere of the next layer, or by a trigonal void covering a sphere of the neighboring layer. So, both ways we can get a tetrahedral void. So, having identified the tetrahedral voids and octahedral voids, let us try to put them together and see what is where. What you find is that in this view of top of the second layer, we find that there are a number of tetrahedral voids. So, all T's written here are the tetrahedral voids, and these O's are the octahedral voids here. And what you find is that if you count the number of voids, we find that the tetrahedral voids are double the octahedral void. It is very significant observation, which we will work on as we proceed further on. So, what you find is that there are twice as many tetrahedral voids as are the octahedral voids. Okay. So, this is a story so far. We have come down to the second layer, but if I have to build up my 3-dimensional structure, I have to go further on. Now, that means I have to put my third layer on top of the second layer. Let us attempt that now. I take the case 1, wherein the tetrahedral voids of second layer are occupied by the third layer. Let us see what happens. Now, what I am showing you here is I am showing you 3 layers now. There is one layer, layer 1, layer 2 and layer 3. In layer 3, what I have done is I have put the third layer in such a fashion, that is, the tetrahedral voids of second layer are being occupied. When I do that, the moment I do that, what I find is that this layer 3 is exactly on top of layer 1. That is, what I am getting is that the third layer happens to be exactly on top of the first layer, and this is referred to as AB repeat. That means, my first layer is typically called as A layer, B layer, and the third layer happens to be exactly same as the A layer. So, it is called as the A. next will be B, A, B, it will build up like that. So, what I will be getting is, I will be essentially getting what is called as an AB repeat structure. Okay. That is my packing in 3 dimension if my third layer occupies the tetrahedral voids of second layer. But here again one has to be careful here that this picture uses different colors to make things clear. What you find is, if I look at a second layer, this is because the second layer has been made red in color here, what you find is that there are 2 types of tetrahedral voids here, there is type 1 and type 2. Type 1 tetrahedral void cannot be occupied by the third layer. The reason being because these tetrahedral voids are located behind the atoms there. So, no atom can go behind and get occupied over there. So, only type 2 will be occupied which are on the top of the second layer. So, type 1 tetrahedral are behind, so they cannot be occupied. So, this is another version of similar kind of picture here. So, this shows you, this is my layer A, layer B and layer C, and layer C is exactly on top of layer A. So, this is my AB repeat. Now, this AB repeat is called as HCP, hexagonal close packing in 3 dimension. This is another attempt to make things slightly more clearer. So, there are few atoms of my A layer. So, this is my A layer covered by the B layer, some atoms are shown there, and then this is my A layer, B layer and C layer, only one atom there. So, we find that C layer or the third layer is exactly on top of the first layer, and this AB repeat, as I just mentioned, gives you hexagonal close packing structure. That is the way we represent that. That is your A layer, B layer and A layer again, and if I just shrunken the atoms there so that I can get the structure well, so you find that that is the kind of structure we have. There is one atom here, there are 6 neighbor, that is hexagonal close pack structure here, and there is the 3 atoms of the B layer and that of the A layer again, they will continue. So, that is the kind of packing we will be generating, that is called as HCP in 3 dimension. So, this AB repeat gives hexagonal close packing structure in 3 dimension. So, that is the way we can represent. This is my A layer, B layer, another A layer and so on and so forth, and if we shrink the atoms, that will look something like this. So, what you find is that this is the kind of arrangement we have in case of hexagonal close pack structure in 3 dimensions when there is a AB repeat. Let us look closely and then find out in such a case the structure which I have been kind of highlighted here, that is the unit cell. Because if you remember that I have been mentioning again and again that unit cell for a given lattice there may be more than one unit cell possible, but the one which is smallest one and which can generate the whole lattice is chosen as the unit cell. So, in case of HCP hexagonal close packing structure, so that is my unit cell in this case. Okay. So, the structure shown here actually is made up of 3 such unit cells there. This is one unit cell, this second will be another one, this will be third one here. Okay. Okay. Let us move further and have a look at, so what is the coordination number in case of HCP structure. We find that this again shows the 3 layers, A layer, B layer and A layer, and this atom has been shown differently. So, that is one central atom I am trying to focus attention to. As I mentioned, in case of a 2-dimensional setup, so this is in touch with 6 neighbors there. So, there are 6 neighbors in the same layer to which this atom belongs. There will be 3 neighbors in the layer preceding that, and there will be 3 atoms in the layer succeeding that. Okay. So, there will be 3 atoms from top, 3 from the bottom and 6 in the same layer. So, there will be a total of 12 atoms which will be touching this or will be in the close vicinity of this atom. That means, this atom will have a coordination number of 12. Okay. So, that is by HCP. Now, let us move further and see that if I go back to the top of my second layer and try to put my third layer on top of it, and in this case now what do? I place my third layer in such a fashion that it occupies the octahedral voids of second layer. If that happens, then what do we get? Then what do we get is, this is my A layer, the first layer, the second layer, the B layer, the third layer, the C layer. Now, when I put a third layer on the octahedral voids, you can see that the octahedral voids are visible here in the background, because they are the kind of hexagonal kind of structures here. When I do that, what I find is that this layer, the C layer or the third layer, so to say, is neither overlapping the first layer nor the second layer. You remember, in case of HCP, the third layer was exactly on top of the first layer. So, in this case we find that this layer happens to be a third independent layer. As a consequence, since it does not overlap second or the first layer, this gives me what is called as ABC repeat, because if I put the fourth layer, there will be only one choice, that is, it will be exactly on top of the first layer. So, what I will have is, I will have A, B, C, A, B, C, that is a kind of repetition I will have here. Okay. So, such a closed packed structure can be shown slightly different with the color differentiation here. So, this is my A layer, B layer, C layer. So, you can see that none of the layers overlap each other, they are different layers by themselves. And if I look at such kind of a pattern, that is called as CCP, cubic closed packing. Now, let us try to clarify ourselves what exactly this cubic closed packing is. This picture actually is an attempt to show that CCP is equivalent to FCC. What has been done here is, that is, there are 4 layers here. They have been differentiated in such a fashion, that is, only certain atoms of these layers. There is 1 atom of my first layer, 6 atoms of the second layer, 6 of the third layer and 1 of the fourth layer. They have been made visible in contrast to the rest of the atoms. As a consequence, what I find is that this looks like an FCC. So, you can see that, that this makes a nice cube here, and these are my face centers here. So, what I find is that CCP is equivalent to FCC. We will elaborate more about it in the maybe the next session, but I can demonstrate it to you with the help of a model here. So, as I just mentioned, I am going to take 4 layers. I have taken one layer, the only one atom of my first layer. Thereafter, what do? I take 6 atoms of the second layer. That is, you choose atoms in such a fashion that there is 3, 2, 1. I purposely done that. I will show you why of this. Then look at the central void and put it through this. Okay. Having done this, what do I do next is, I take this is my A layer, this is my B layer. Now, I take the C layer. Here again I take 6 atoms. And when I take 6 atoms, again 3, 2, 1, but now I put them in the order opposite to the previous one. I had put it like this 3, 2, 1. Now, I take in the opposite sense 3, 2, 1, put it into this. And lastly, what do? I take one more atom of my fourth layer. When I do that, what do I get is, so I have basically used 14 atoms, 1 of layer 1 A, 6 of layer B, 6 of layer C and 1 of layer A again. And let me just hold it here and tilt it a little. What do you see? You see a nice cube. You see, this is my the front face of the cube here, this is my face center. Look at this second face, look at the third face, look at the fourth face, the fifth face. You find that CCP is nothing but my FCC. Okay. So, I will elaborate more on this in my next session. But basically, the point I wanted to bring home here is that if I do make a closed packed structure in 3 dimension in such a fashion that I have got A, B, C repeat, then I will be essentially getting what is called as an FCC lattice. And there are a lot of structures which can be understood in terms of my FCC lattice there, FCC unit cell. So, we will elaborate more on this as we move into next sessions and all. Now, here again, like in case of my HCP, hexagonal closed packing in 3 dimension, here also the coordination number is 12. So, we find that there is nothing much of explanation required here. So, there is one atom here, 6 neighbors in the same layer, 3 neighbors of the preceding layer, 3 neighbors of the succeeding layer. That means, this is my B layer. So, A layer and C layer, 3 neighbors are there. Again, the coordination number is 12. But we had to make a small differentiation between HCP. If the things are similar, then what is the difference between HCP and CCP? Let us see the difference here. Now, when we had AB repeat, what we had was, there are 6 neighbors in the same layer, fine, here too the same thing is there. But if you look at layer A and layer A here, so they are identical. whereas in this case the orientation, this is pointing away from you, this is pointing towards you. So, that is a basic difference between, because this is my A layer, this is C layer. In this case this is A and again A. So, that is the basic difference between the two kinds of packings there. So, this is my hexagonal close pack structure. It gives me a different kind of unit cell, which we will not talk more about, because there are not very many structures which can be understood from here, but this is my main thing which I want to elaborate on in the next session, where I will talk about ABC repeat or CCP structures, which basically I have just shown to be equivalent to FCC lattices. Okay. Let us try to quickly run through what we have done today. What we have done today is we reviewed what we did previously, thereafter discussed the need to learn about close pack structures. Why do we need to know about it? Thereafter we explained the generation of close pack structures in 2 dimension and 3 dimension. Thereafter we described that, you will recall that we did talk about the kinds of voids we have, trigonal void, tetrahedral void and octahedral voids, etc. And then we have seen also that when I extend my packing to 3rd dimension, what kind of packed structures we get. One is of the AB repeat type, the other one is of ABC repeat, and in both the cases we have seen the kind of unit cells we come across. Now, as I just mentioned, in the next session we will try to analyze this, we will build on the equivalence of CCP and FCC. So, we will look closely into my FCC unit cell and analyze that little further in terms of the types of voids, how many of them are there, where are they located, and then how do I use this CCP FCC equivalence to decipher or to rather describe the structure of wide variety of solids there. So, that is